So this is the work that I did, or that I'm doing in Oxford, together with Peter Düben from ENES-RI, Dr. Smolakevich from MCAR, and of course Tim Palmer, who holds the ESC grant that I'm supported by. And I'm going to take you along a bit of a deep dive into dynamical core development. And the specific dynamical core I want to talk about is the semi-implicit approach. And in semi-implicit time stepping, that has become quite popular over the last couple of years, parts of the equations of motion are done explicitly, while other parts are done implicitly. And these other parts are typically gravity waves, so fast waves and sound waves. And that leads to a large model time step. But the disadvantages or the problem is a bit that you need to do an expensive implicit height or pressure solve each time step. And how is this usually being solved? So the problem is can basically be written as an A phi equals B problem. So B being a vector, A being a matrix, and your fluid thickness or your pressure phi also written as a vector here. And the matrix is square, positive, definite, and non-symmetric. So you know the problem has a unique solution phi star. But how do you solve this problem is a bit of a question. So direct inversion of A is impossible simply because of the dimensionality of the problem. If you think about it for operational weather forecasting system. So instead, iterative solvers are used, or iterative linear solvers are used. And here we especially talk about Krylov subspace methods. And what the iterative solver tries to do, it tries to reduce the mismatch in the linear equation here. So it tries to reduce this Ri, the residual error. And if you deem your residual error small enough, usually this is done via some kind of exit conditions, you take your fluid thickness of this solver iteration and you set this as your new fluid thickness or your new pressure at the next time step. And the motivation for doing machine learned preconditioners is basically that the preconditioner is one of the crucial parts of computationally efficient linear solver. But at the same time, it's also quite an expensive part of the solver. And the preconditioner is doing an approximate inverse using incomplete information about the problem. So you have this whole idea of uncertainty already ingrained into the basic problem. And one of the advantages, if this actually worked, would be that the machine learning application is actually part of the whole linear solver, which is in itself has quite strong fundamentals and could counter potential robustness issues that you sometimes have with machine learning. Because what basically happens is that the solver controls whether your error, your residual error field is small enough. And if the machine learned preconditioner would fail at speeding up the convergence, it would just not exit the solver and you would know that something went wrong. So why do we even need a preconditioner and what does it do? So for these linear solvers, for these iterative linear solvers that I talked about, usually the condition number of this matrix A determines the convergence rate by quite a large degree. And this condition number is, in our field, it can be seen as a squared ratio of the largest to the shortest wavelengths. And if you think about large global waves, and at the same time about these small waves that you can encounter in the vertical grid, you see that this number is really, really large in MWP. And so if you just take a standard out-of-the-box iterative solver, it might not even converge at all because the increments are below the machine epsilon. So what you do instead is you use a preconditioner, and the preconditioner is basically trying to find a matrix A tilde so that the condition number of your combined matrix is smaller. So basically you reformulate the problem mathematically by adding or by multiplying here left side preconditioning. So you multiply from the left with this A tilde. And so you got a new, mathematically, you got a new linear problem to solve. But the problem is that this inversion needs to be done each solver iteration. So the inversion needs to be really cheap because the overhead of the preconditioner needs to be added to the linear solver. So coming up with good preconditioners is really hard. And this is where this idea of machine learned preconditioners comes in. So you can write down what a preconditioner is actually supposed to do if you think about the optimal choice of A tilde being the matrix A itself. Of course, like in practical purposes, this would never work. But you can write down what it's actually doing. And you see here that this preconditioner, the inversion, is actually applied to the residual error here. And what this gives is the increment in fluid thickness or fluid pressure. So the preconditioner actually tries to map between this residual error field to the increments in fluid thickness. And this leads to the idea that we could train a neural network or some other machine learning algorithm to actually perform this mapping that we're looking for. And the idea would be that as inputs, you use local stencils, so neighboring values of a grid point of the matrix coefficients of A and these residual values. And as output, you just look for the grid point value of height or pressure increment delta phi. And our test bed is a shallow water model. The discretization is based on the MP data advection scheme for momenta, which is Eulerian, here Eulerian and second order corrected. As a linear solver, we use a generalized conjugated residual method of order 3. And we do this work on a latitude-longitude grid. Typically, you try to avoid the lat-long grid. But here we especially choose it because we want to study what happens near grid singularities. And also what comes with these grid singularities is that you have very, very, very small zonal grid spacings. And as a reference preconditioner, we define a semi-implicit Richardson preconditioner. And this works as follows. So first we take the preconditioner to be our original matrix A. Then we omit all cross-derivative terms, split the matrix into 3 parts. So a zonal part, a Helmholtz part, which is basically the center point, and the meridional part. And then we can perform a Richardson iteration to get an estimate for the fluid thickness. And you see here that the zonal part and the Helmholtz part is actually done implicit. So for this Richardson iterations, it has the time index n+1. And the reason we're doing this is that the zonal part is where the stiffness of the matrix resides in a latitude-longitude grid. And this will speed up the linear solver quite a bit. And our model setup or test case is zonal geostrophic flow around the scaled down real Earth topography. For the first case, we just used a 5.2 degree model resolution and 120 days of integration time. And you can see snapshots of fluid thickness for several days, like after 15 days, 50 and 120. And in the absence of potential energy restoring, you see that the flow is slowly decaying. And our neural network setup, or our machine learning setup, is that we use 3 different machine learning techniques. So the first one is simply a linear regression. The second one is neural network fully connected with 1 hidden layer and 5 neurons in that layer. And the second one, the third one being 5 hidden layers and 200 neurons in each layer. The activation function is simply ReLU. And this is these are trained on the first solver iteration for days 15 to 120. We train 1 neural network per latitude, and we train different input stencil sizes. So we take 1 neighbor or 2 neighbors. And the input is then 7 input stencils, 6 for the matrix coefficients, because we have a generalized Laplacian, and 1 for the residual error field. And the output, as I already said, is a single grid point value of the increment in fluid thickness. We use about 1 million training examples and 500,000 validation examples. And if we look at the first results, so this is basically how much could the error in fluid thickness be reduced by a single application of the preconditioner. And in blue, you see here's a reference, which is the semi-implicit Richardson, the analytical preconditioner. In green, you see the linear preconditioner, so the linear regression model with a small stencil, input stencil. And in red, solid red, you see the linear regression model with 5x5 stencil, input stencil. And what's quite surprising, but what came out of this is that that actually using deep neural networks didn't really give us an edge at all compared to linear regression. And so what we brought back into the model, or what we implemented back into the model, was this solid red line. So the linear regression model with a 5x5 stencil, because it performs as well as the other ones, but is extremely cheap computationally. And these are convergence results that we got for our model for days 15 to 120. And what's shown here is, like on the y-axis, you see the residual error, or some norm of the residual error. Here's the infinity norm. And on the x-axis, you see the solver iterations that were required. On the right, you see the semi-implicit Richardson preconditioner. So this is a preconditioner that's our analytical reference preconditioner. Down below, here's what happens if you do not have a preconditioner at all. And on the upper left here is what our machine learned preconditioner is doing. And what we see is that the convergence rate is consistently high for all solver iterations. And that no point during training was data from these later solver iterations seen at all. We do not get the exact performance of the semi-implicit Richardson preconditioner, but we also have to take into account the overhead, and there's a linear preconditioner is quite cheap. So here's another convergence plot where we actually looked at days, in simulation days 1 to 14, and these were not part of the training set at all. So we're looking at the spin-up phase where you potentially have shocks from model initialization. And even here, the linear regression model with the 5x5 stencil is acting as a good preconditioner. And in summary, the machine learned preconditioner needs to have learned some general rule about predicting the fluid thickness increments delta phi. And the good thing about having this really low complexity machine learned preconditioner is that we can actually analyze it, so we can actually interpret what's happening. And so here you see the relative contribution of the linear regression that's applied to the residual error field. The relative contribution of the 6 matrix coefficients was not shown here because they turn out to be negligible at all, completely. So there's no relative contribution coming from these. And what we see is that there is actually the imprint of the system matrix A. So you can see these 5 points, and this is basically your spatial discretization showing up again. And if you only take these 5 points or these 5 inputs, the machine learned preconditioner is actually a lot cheaper per application than the semi-implicit Richardson. So in the end, they basically come out to the same performance, even though the machine learned preconditioner needed a bit more iterations. And
Dan, you have 2 minutes left?
Yeah. In a second step, we increased some complexity of the model setup. So we went to a much higher resolution of 0.7 degrees. We went to real topography, so steeper gradients, smaller thicknesses, which leads to a much harder flow in general. And we reinitialized, so the flow does not decay. And we introduce polar absorbers, which enables us to take a much larger time step. And for people who know about this approach, the effective Coron number becomes close to the numerical limit of 1. And even with this, we get good results when using a hybrid preconditioner. So we use the approach that we also presented previously, now between 70 south and 70 north. And for the remainder, we use the semi-implicit preconditioner. And this gives us an expected speed of factor 2 compared to the pure semi-implicit approach. Unfortunately, we can't use this approach near singularities, so the linear regression model with a small stencil does not work. And we do not find any improvement when using larger neural networks. And secondly, what happens if we use larger input stencils for the parts near the poles? Well, it kind of works a bit better, but the convergence rate goes down quite a bit. And so it's not perfect yet, but what's interesting is that the convergence rate for the first iterations is really good, and then it just kind of dwindles down. And so we think that there might be further improvements possible. And with that, I come to conclusions. So the preconditioning can be done for weather and climate models with machine learning. Performance was good. So it's we find that performance is comparable, or with a hybrid preconditioner approach, it's actually more efficient. Due to the low complexity, the preconditioner can actually be interpreted. These results are on arXiv, and the next step is to investigate these machine learned preconditioners for ECMWF's IFS VM. And thank you.